Good evening to you all. I believe that you could all hear me. All right, so today we'll be looking at complex numbers, which is one of the subtopics in algebra, the course that most engineering students are doing in first year. So we want to look at complex numbers. Now, we know in the real number system, we would have several forms of numbers, and complex numbers is one And complex numbers is one of the number system that we want to talk about. Now, in complex numbers, there are I'm coming. In complex numbers, there are several forms of representation. So we want to look at the rectangular representation of complex numbers. So for the rectangular representation, we could have, let's say, z is equal to x plus iy. Now, our x that we have here, we see is the real part or the real number system. Now, our y that we have here is imaginary. So in senior high school, you realize that when we are solving for the roots of a quadratic equation and we have something like x is equal to square root of -1, we say it does not exist. That is the senior high school mentality. But here, because complex numbers, forgive me for this notification, because of complex numbers being part of our physical system as engineers, so physical system, so if we take, sorry, so if you take, let's say, an electrical circuit where there is flow of charges, this phenomenon of imaginary portion of numbers comes into play. And so for that, there is a need for us to look for a way to represent these numbers. And so we use the symbol I to represent complex numbers, which is I is equal to square root of -1. So anytime you see I attached to a number, it means that that number is in the complex form, or it's a complex number. So for instance, if we are asked to find the square root of, let's say, -64, so here we are not going to say it is undefined, but we can represent -64 as square root of -1 times square root of 64, right? And we know that square root of -1 times square root of 64, so this is going to give us square root of -1 times what? 8. And we know that -1 is what? I. So this is going to give us 8 what? I. Are you okay? So basically, this is what complex numbers is all about. All right, so let's look at something here. I want to erase this portion. I want to erase this portion so that we could look at something different. All right, so if I have a complex number I, which we know is square root of -1, if I have I squared, we know that it's going to be square root of -1, everything squared, and that is equal to what? -1. If I have I to the power 3, that is I cube, which is equal to square root of -1 squared times square root of -1. Now we know that square root of -1 squared is going to give us -1, and square root of negative 1 is what? I. So this is negative I. If I also have I to the power 4, which is square root of negative 1 all squared times square root of negative 1 all squared. This is going to give me negative 1 times negative 1, and that is going to give us 1. So let's keep this in mind. If I have I to the power 1, it is I. If I have I squared, it is negative 1. If I have I to the power 3, it is negative I. And if I have I to the power 4, it is equal to what? 1. Now, the reason why we have to know this is that in exams, you could see some lecturers giving I to the power 27, and you need to choose an answer. So I to the power 27, we could see that I to the power 4 is what? 1, right? So we can multiply this by 6, which is I to the power 24, right? So the next, if we continue from here, that is I to the power 24 is what? 1. Then 25, I to the power 25. So we just add an I squared, sorry, an I to it. That will give us negative, sorry, negative 1. If you add another I, um the next I is going to be, you multiply it with the next I is going to be positive what? 1. So you need to know how to go about with these things. So it's very, very important. Let me let's see. uh, so let's take an example of what I just illustrated here, so that we see how we can do it at a faster pace. So assuming we are given I to the power 27 to compute, right? We know that I to the power 4 is 1, I to the power 3 is negative I, and I squared is negative 1, and I is still I. So if you are given this, we can break this one down as I to the power 4, right? By I to the power 4, by I to the power 4, by I to the power 4. And this is what? 1, 2, 3, 4. That is, when we add the exponent, because of indices, when we add the exponent, that is 16. I can add I to the power 4 again, that will be 20. By I to the power 4 again, that will be 24. Now, this is what? 1, right? Times 1, times 1, times 1, times what? 1. And that is what? 1. So I to the power 24 is what? 1. But we are left with I to the power 3 to make it 27. And we know that I to the power 3 is what? Negative I. So we just multiply this to this, and I to the power 27 is equal to negative 1. I. As simple as that. So you need to know how to find a way out of such questions. Let's take another one. Let's say I to the power um 30. You are giving I to the power 30 to evaluate. Now we ended at I to the power 4 to be 1. But if I have I to the power 5, what is it going to be? I to the power 5 is going to be 1 times what? I, right? That is I to the power 4 by I. And that is 1 times what? I. And that is what? I. So I to the power 5 is what? Positive I. So if you are giving I to the power 30, I can say that I to the power 5 by 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 I to the power 5. This 1, 2, 3, 4, 5 by I to the power 5. That is 6. And that will give us 30, right? Now, I to the power 5 is what? I. So here, let me use a different color so that we could clearly see it. So this is I. This is also another I. This is also another I. This is also another I. And this is also another I. And this is also another I. And so we have this the first I. This is the first I. So we have 1, 2, 3, 4, 5, 6. Right? So that is going to give us I to the power of 6. And we know that out of I to the power 6, we can get I to the power 5 by what? I. And I to the power 5 is what? I. So I by I, and that is what? Negative what? 1. So when we are asked to find I to the power 30, it's simply negative what? 1. And that will end this part. So we will continue. I'm trying to move to the next page, but having some challenge. So I have to erase. So that we continue. Let me increase the size of the eraser so that see. So we've looked at powers of I. So the next thing that we are going to do, we'll look at addition. Look at the addition and subtraction. Remember that we are looking at the rectangular form of complex numbers, which is the easiest part. Now, if I have complex number 1, which is a plus bi, and complex number 2, which is c plus di, and I have complex number 1 plus complex number 2, it's simply a plus bi plus c plus di. So in addition of complex numbers, the real part will add itself, and the complex part will also add what? Itself. So we are going to get a plus c. I'm going to get a plus c, which are the real side, plus what? The complex side, bi plus what? di. So anytime we are asked to add or subtract complex numbers in the rectangular form. So this is the rectangular form of complex numbers that we are talking about. So anytime you are asked to add them, you just take the real part, you add it, and what? The imaginary part. The imaginary part is the part that has the I with it. So this is the imaginary part. So in this case, you just group like terms, just as we've been doing. Grouping of like terms. They said now they are boom. So here you see the A and the C are like terms, and the eyes people are also what? A like term. So let's take an example here. Hope I'm not going too fast. If you feel I'm going too fast, you can share your comment in the comment section. You can share your comment in the comment section if you feel I'm going too fast. Let me clean this part. Okay, so let me use a red color for distinguishing. So I have an example. Complex number 1 is 2 plus 3i, and complex number 2 is 4 minus 5i. So in this case, we are asked to find z1 plus z2. And so I have 2 plus 3i plus 4 minus what? 5i. Now grouping like terms, the real part 2 plus what? 4. Then the imaginary part 3i minus what? 5i. So I'm going to get what? 6 plus what? Minus 2i, right? If you are confused here, you can break it down as this. If you are confused at this part, you can break it down as this. Factorize I out. You'll be left with 3 minus what? 5, right? And that is what? And that is minus 2 times I, and that's minus. That's what I've got in here. An example, another example. I have complex number 1 is 10 minus 16i. Complex number 2 is 5 plus 8i. We are asked to find z2 minus z1. Now here you have to be careful. In all this, we are preparing for Midsem. Some lectures are very tricky, so you have to be smart. You see, always we bring z1 plus something or z1 minus something, but here I brought z2 minus z1, so you have to take note. So z2 will come first. So this is z2. So z2 will come first. That is 5 plus 8i minus the expression 10 minus 16i. Please, this negative will affect the whole of what? Z what? 1 or the first complex number. So the negative is multiplying the whole complex number. That is the 10 minus 16. So I'm going to get what? 5 plus 8i minus 10 plus 16i. So here too you group like terms. The real part to be at one side, that is 5 minus 10. Then the imaginary part to be at another side, that is 8 plus what? 16i. And this was going to give us minus 5 plus this was 24 what? I. And that will be it. So that this will be the end of addition and subtraction of complex numbers in the rectangular form. Now, these ones are very simple. You could even use your calculator for that. So you could get some YouTube videos on how to. Unfortunately, I can't do it here because of the system. So maybe in person, if there is going to be an in-person tutorials, we teach you guys on that. These are very simple and you could easily use your calculator for it. So let's look at another thing in complex numbers. Let's look at multiplication and division. Multiplication and division. Sorry, my spellings. And division. Now here too, we are looking at multiplication and division of complex numbers in the rectangular form. In the rectangular form. Remember something called, now complex numbers is like said, or complex number is what? A negative one under the radical sign or the square root sign. And so it takes the properties of said, right? So we have to keep something in mind, which we mostly call conjugate of said, right? So if I have, let's say, square root of 2, the conjugate is going to be negative square root of 2, right? So let's put this at the back of our head, especially when we come to the division. So now we want to look at multiplication. So if I have complex number 1, which is a plus bi, and complex number 2, which is c plus di, and we are multiplying, that is z1 times z2. And so you know your binomial expansion, which is a plus bi multiplying c plus di. So there are so many acronyms for this kind of multiplication. Some people call it the PEDMAS and the rest. So you just take one, use it to multiply what is here. Take what is here, use it to multiply what is here. So this will be the system. So that this is how we multiply. So it's going to be a multiplying, we're going to have a multiplying, oh, oh sorry, let me erase this. A multiplying c, right, plus a multiplying di. Then we take bi multiplying c plus bi multiplying what, di. So these are real numbers multiplied. That will give us AC plus a real number multiplying a complex number, imaginary number, that is ADI, plus an imaginary number multiplying a real number, that is BCI. They will all carry the I. Then here you've seen two imaginary numbers. So we are going to get B multiplying D. Then what? I will multiply I, right? And so we are going to finally get AC plus ADI plus BCI plus BD minus 1. Because I by I, or I squared, is what? Negative 1, right? So we are going to get AC. This will then turn into what? A real number, right? So minus BD. Then the complex people will go and do their thing. ADI plus what? BC what? I. So that is how we multiply in complex numbers. That is the multiplication system in complex numbers. As easy as that. I hope there is no one there out there with understanding challenge. So in real terms, what we are saying that anytime we multiply two complex numbers, we mostly end up getting a real part and an imaginary part. There are instances where you are going to get only real parts. There are some instances where you are also going to get only imaginary parts, especially when some of the things tends or end up becoming zero. So let's take some example. Example one, I have zi is equal to 2 plus 3i, and z2 is equal to 4 plus 5i, and this is multiplying. So z1 times z2, and that is 2 times 3. Sorry. Oh, let me erase this. Forgive me. Mm. So 2 plus 3i, right, times 4 plus what, 5 what, I. So we take 1, use it to multiply. So it's going to be 2 times 4 plus 2 times 5 what, I, plus 3i by 4 plus 3i by what, 5 what, I. And so I'm going to get 8 plus what, 10i plus 12i minus 15. Why? Because 3 times 5 is 15. I by I is what, negative 1. That is why it becomes minus 15. So I'm going to get 8 minus 15 plus 10i plus 12i. We've already learned how to add and subtract complex numbers. So you just group like things, all the real numbers at one side, the complex numbers, the real numbers at one side, and the imaginary part also at one side. And so this is going to give us minus 7 plus what? 22 what? I. Easy, easy, very easy. Especially the rectangular part of complex number, very, very easy. So yes, this one aspect of it. Let's take another example. Let's take another example and we move on. Another example under the multiplication. So example 2, I have complex number 1 is 4 minus 5i and complex number 2 is 3 plus what 2i. We are asked to find the product of z1 and z2. So we are asked to find the product. So in finding the product, we are saying that we know what product is multiplication, z1 by z2, and that is 4 minus 5i multiplying 3 plus or 2i, right? So if I multiply 4 times 3, so 4 by 3 plus 4 by 2i, then minus what? 5i multiplying 3 minus 5i multiplying what? 2i. And so I'm going to get what? 12 plus what? 8i. That's good. Minus 15i. Then what? Now here, see the trick. Let's deal with the the numbers first. So that is 5 times 2, right? And that is 10. Then I by I, that is negative 1, right? So if we cut this side, we have what? Negative 10. But in front of it, there is a negative number, or there is a negative coefficient. And so negate, that will be what? 4. That will be 10, right? That is 10. So I hope you are not confused. If you are confused, let me know in the comment section. So you are going to get grouping like 10. You are going to get 12 plus 10, right? That is the real part, plus 8i minus 15i, right? So if I continue, I'm going to get what? 22 8i minus 15i, that is negative 7 what? I. And that is my final answer. As simple as that for multiplication of what? Complex numbers. Now let's look at what we call theorems. There are some things that we need to know them. So let's look at some theorems concerning multiplication of complex numbers. It will aid us, very, very important. All right, so let's look at some theorems. The first theorem is the first theorem is, if I have a complex number z, which is x plus yi, the conjugate is what? X minus what? Y. I told you that in senior high school, in said, we know that if I have square root of 2, the conjugate is negative square root of 2, right? If I have negative square root of 2, the conjugate is positive square root of 2. So if I have yi, its conjugate to be what? Negative y what? I. It is the imaginary part, the imaginary part that brings in the properties of conjugation. So if this is a complex number, this will be its conjugate. And we are saying that a complex number multiplying its conjugate will always give you the magnitude of the complex number squared. What are we saying? Okay, let's put it in practice. So let's see. If I have z is equal to 3 plus 4i, its conjugate is 3 minus what? 4i. So let's see. Let's multiply the complex number and its conjugate. That is 3 plus 4i multiplying 3 minus 4i. So taking 3 to multiply, that is 3 times 3, then plus 3 times minus 4i, plus 4i multiplying 3, plus 4i multiplying minus 4 what? I. And this is what? 9 minus 12i plus 12i plus 16. I'm sorry, 16, not 16i, plus 16. Let me erase that. So you realize that we are going to get what? 9 plus what? 16, because this and this will go to 0. And this is what? 9 plus 16 is what? 25. So we are saying that if I have a complex number like this and I have its conjugate, it's equal to the magnitude, that is magnitude of 3, or sorry, how do you call it? Uh, did I say magnitude? Sorry, the absolute. Absolute. Uh, the symbol looks alike. So sorry. It's absolute, not magnitude. So if I have 3 plus 4i as my complex number, and this is its conjugate, and we are asked to multiply it. So in exams, you not be told that it is a conjugate. You should see with your eyes. How do you see? You realize that all the terms are equal, or they are the same. That is the real part 3 3, the imaginary part 4 4, I. But if you look at the imaginary part, there is a positive and what? A negative. So this is what will inform you. You get it. You get to know that this is what? A complex number, and it will conjugate. And if they are multiplied, I just take the what? The real part, square it, plus the imaginary part, I take the number, just the number, then that one too, I square it, right? And that is going to give me what? 9 plus what? 16. And that is what? 25. So anytime we are given, or we are asked to find the product of a complex number and its conjugate, you just take the individual numbers, square them, and or sum them, and make sure that you find the absolute of their sum. Also, another how do you call it, theorem that we need to know is, so this is the first one. The second one is that if I have a complex number, that is z, being added to its conjugate, it will always give me 2 times the real part. 2 times the real part. So let's see. If I have example, let's give an example. If I have z is equal to 6 plus 5i, what will be the conjugate? Tell me in the comment section. Right? 6 minus 5i. That's right. So, excuse me. So, if we have z plus its conjugate, which is 6 plus 5i plus 6 minus 5i, grouping like this, I'm going to get what? 6 plus 6 plus 5i minus 5i. And this is what? 12. This will go to what? 0, right? And so we are saying that if I have a complex number and its conjugate, add them, it's equal to 2 times the real part. So the moment I see in a question, maybe z1 is equal to maybe 5 plus 15i, and maybe z2 is equal to, let's say, 5 minus 15i, then I will not waste time. I just 2 times what? 5, and so 10. You get it? Don't waste time, because KNUST exams, you know, but time would not permit you. So yes, we have to know these things. Very, very important. And some of the questions too, they like to ask these theorems, especially if your lecturer is Dr. Kwabi. You'll be doing English rather than mathematics. So let's continue. The third axiom is, or theorem is, if I have a complex number z, then minus its conjugate, it is equal to 2 times the imaginary part without the I. The imaginary part without the I. Without. So let's see. Let's take an example to confirm it. Let's use this example. Let's use this example. The example, how do you call it? Anyway, let's use this example. Okay, let's see. So Z1 is 6 plus 5i. I want to see if the I will be part or the I will not be part. Z conjugate is 6 minus 5i. So we are finding this, right? And so we are going to get 6 plus what? 5i minus 6 minus 5i, right? So we are going to get 6 plus 5i minus minus 6 plus what? 5i. So grouping like that, you have 6 minus 6 plus 5i plus what? 5i. And that's going to give us 0 plus or 10i. So the I should be part. So just 2 times the imaginary part with your I. Do you get it? So you could see that here the imaginary part was what? 5i, right? So because this and this are conjugate and we are subtracting the conjugate from the main complex number, then you just move straight. Don't go and waste your time to do what I did here. You just move straight by multiplying 2 to the imaginary part. All right. So the next thing that we do, so with these axioms in place, let's look at, so these three axioms, that is, if I'm multiplying a complex number and its conjugate is equal to the magnitude, the magnitude of the complex number. If I have a complex number being added to its conjugate is 2 times the real part. If I have the conjugate of a complex number being subtracted from it is equal to 2 times what? The imaginary part. As simple as that. Make sure to bring your I. Now let's look at the division. Division of complex number. Here we would employ the some tools under rationalization of said. Very important. You know that a set cannot be a denominator. So that is basically what it is. So division of complex numbers. So here we are focusing on division of complex number or complex numbers. Division of complex numbers. So if I have a complex number, let's say Z1 is A plus BI, right? Then I have Z2 is equal to C plus DI. And we are asked to evaluate Z1 over Z2. Z1 over Z2. You know that Z1 is A plus BI, Z2 is C plus or DI. Now what is DI? DI is D by square root of minus 1, right? You know that. And what is this? This is a set. A set in mathematics principle cannot be part of the denominator. So we have to what? Rationalize it. And you know how to do it. You have to rationalize the denominator. So in doing so, we have A plus BI over C plus what? DI. Now in rationalizing denominator, you take the denominator that you have, look for the conjugate. So this is our denominator. The conjugate of it is what? C plus sorry, C minus, not plus. C minus. So it's going to be C minus what? D what? I. So this is the conjugate of the denominator. Now, if I have this, then rationalize, I have to multiply the numerator and the denominator by this conjugate, So I'm going to get A plus BI over C plus DI multiplying C minus DI over C minus what? DI. Yes. Now I've not done anything new to it because this is one, right? This whole thing. Let me use my A. This whole thing is one. This whole thing is one. So I've taught you how to multiply fractions. So sorry, multiply complex numbers. So if I extend it, I have A plus BI, this expression multiplying C minus DI all over C plus DI multiplying C minus DI. What can you see down here? Let me change the color. What can you see down there? You could see a complex number being multiplied by its denominator. Hey, sorry, conjugate. Its conjugate. And we learn from the earlier theorems. That if we have if we have a complex number multiplying its conjugate, is simply the what? Take the real part, square it, add it to the imaginary part and square it. So this will come in hand. So I have A plus BI multiplying C minus DI all over C squared plus what? D what? Squared. And that will make your work a little bit faster. So let's take some example. Let's take some example. Let me clean this part of the board. Let me clean this part of the board. Let's come here. Let's come here and take an example. So example one, let me give example one. I have a lot of questions here, so we'll see. So we have 3 plus 2i over 1 minus 3i. Now this is the complex number that we are supposed to evaluate or simplify. Now 3 plus 2i over 1 minus 3i. So far as the denominator has an I in it, it means we have a radical sign as a denominator. And so we need to rationalize it. So we look for the conjugate. We have I minus 3, 1 minus 3i. The conjugate of it is what? 1 plus what? 3i. So we take the conjugate used to multiply the numerator and the denominator. So we have 3 plus 2i all over 1 minus 3i multiplying 1 plus 3i all over 1 plus 3i. And so this is going to give me 3 plus 2i multiplying 1 plus 3i all over. Now here we have what? 1 minus 3i multiplying 1 plus 3i, right? And so from here, we could see that, let me change the color so that you see the beauty. So we could see this, right? This is a complex number that we have here. And this is what? Its conjugate. Remember, complex number times its conjugate is equal to the real part squared plus the imaginary part squared without the I, right? And so this is going to give us 3 plus 2i multiplying 1 plus 3i all over. I'll take this 1, that is 1 squared, plus I'll take the 3, which is what? 3 squared, and this is going to give me what? Then I do my computation at the top. This times this and this times them, right? So I have 3 times 1 plus 3 times 3i. Then plus 2i times 1 plus 2i times what 3i all over 1 plus what 9. And so this is going to give me 3 plus 9i plus 2i minus 6, because 2 times 3 is 6, I times I is what minus 1 all over what 10. And so if I continue, I'm going to get grouping items, 3 minus 6 plus 9i plus 2i all over what 10, which is equal to minus 3 plus 11i all over what 10. And this will be our answer for this question. Very easy, very easy, but you need to be fast. You need to be fast about it. Let me pan to this place so that we could use it for another example. A very simple example. Let's see. Okay, let's take example 3. Let me take example 3. Then we go to argan diagram. Then we can enter the polar representation. Remember, what we are doing is complex numbers in the rectangular form. So let's look at this example. 4 minus 5i all over 2 minus I all over 2 minus I. So this will be equal to, because we have this an I there, we need to rationalize the denominator. We have an I here. We need to rationalize the denominator. So we look for the conjugate of this, and the conjugate is 2 plus what I, right? So we take the conjugate, use it to multiply the numerator and the denominator. So we have 4 minus 5i over 2 minus I, multiplying the conjugate of the denominator is this, so which is 2 plus I all over what 2 plus I. So I'm multiplying the numerator and the denominator. And so I'm going to get 4 minus 5i multiplying 2 plus I all over 2 squared plus 1 squared. You know the trick there, right? You know the trick. I've already established the trick. This and this, they are conjugate. And you know that z by its conjugate is equal to the x squared plus the y squared, right? This is my x and this is my y. The coefficient of the I is 1, so 1 squared, right? So I will multiply and I'm going to get 4 by 2 plus 4 by I minus 5i by 2 plus minus 5i by I. And this, everything is 4 plus what? 1. And this will be equal to 8 plus 4i minus minus 10i plus 5i, because I by I is negative 1 by negative 5 is positive, right? So this will be over 5, and if I continue, I'm going to get 8 plus, without an I here, there will be no I here. So there will be no I here. Because the I times I will give me negative 1, and that will multiply the negative 5. So I'm going to get 8 plus 5 plus 4i minus 10i all over what 5, and this is equal to what 13 minus 6i of this 30 minus 6i all over what 5. So you can take the question and the final answer. There's the final answer, and try your hands on them. And try your hands on them. All right. So we are basically through with complex numbers involving or complex numbers in the rectangular form. We've looked at the addition, their subtraction, their multiplication, and their division. Now we want to enter into the senior man, that is the polar representation of complex numbers. Here is the senior man because you very soon find out. But it's very easy, very simple. If you have time for it, it comes in hand. So we have to first of all look at the graphical representation of complex number. If we want to um, usher ourselves into the polar form of complex number, we need to understand the graphical representation. So the graphical representation. So graphical representation of complex numbers. Of complex numbers, which is mostly called the Argand diagram. Now, in complex numbers is like fractions. You can have fractions in decimal form, in percentage, in common fraction, and the rest. Complex numbers too, we can have it in several forms. You can have complex numbers in the rectangular form. That is what we did. Rectangular. That is a plus bi. Can have complex numbers in the polar form, which is let's say 2 comma let's say 30 degrees. We can have complex numbers in the Euler form. That is maybe 2 e 2e, let's say 2e, maybe 2i, maybe 2e 2i. So what we are going to do is simply going to learn how to convert from here to here. That is from rectangular to polar, and from polar to Euler, or from Euler to polar, or from Euler to rectangular. Please, the pronunciation of this word depends on the school that you attended. I went to Kufuri as a tech. English teachers, you understand. So I call it Euler. Yeah. So depending on what we want to do, so we are just transforming complex numbers in the rectangular form either to the polar or to Euler, or from Euler to polar, or from polar to how do you call it, rectangular. So basically that is what we are complex numbers is all about, in terms of the mathematics behind it. So we want to look at the Argand diagram. Now is we have the Cartesian plane, but that's what we mostly know, but this is not the cardinal point. So the Cartesian plane. Then we have our imaginary axis. So what we mostly know as the y-axis is now imaginary axis, and what we know mostly as our x-axis. Why is this thing doing this? Give me a minute. I'm coming. Okay. Okay. All right. So let's continue. All right. So the y-axis will be our imaginary axis, and the x-axis will be our real axis, right? So if I have, excuse me, if I have a complex number, x is equal to 2 plus 3i. Now, this axis, is the positive real axis. This part is the negative real axis. So this is negative, this is positive. This part is positive, this part is negative. Let me put the arrowhead, negative, negative. So if I have a complex number like this and we are asked to plot it, assuming this is my origin 1, 2, 3, 4, 5, I have points here 1, 2, 3, 4, 5 here. Now, and I'm supposed to plot this point, right? That is, the real part is 2, the imaginary part is 3. So real part is 2. Here's my real part axis. This is my axis. This is my 2. Then I have to trace it to my imaginary part, which is what, 3. And so the line, and so this line, so this is the point. So the distance from the origin to the point is what we call the magnitude. Magnitude, magnitude, right? Then the angle here, you see, there's an angle that is made with the real axis. The axis that the real numbers are on. And that angle is what we call the argand. The argand. The argand. The angle that is made with what? With the real axis. That is the argand. When we begin complex numbers in the polar form, we would understand it. We would understand it better. You understand it better. So we have to know how to plot uh, complex numbers in the rectangular form. We have to know how to plot it in the Argand diagram. So let's see. We take some examples, then we move. So let's see. Let's take some examples here. Let me example 1. So draw an Argand diagram to represent to represent to represent the vectors or complex numbers. So these complex numbers are in the rectangular form. So I have a complex number. Z1 is 4 minus 3i. Z2 is 4. Z3 is minus 6i. Z4 is 2 minus 8i. Z5 is I. Right? Z6 is, let's say, 10 plus 5i. So we have these complex numbers to represent on the Argand diagram. So let me draw my Cartesian plane here. Let me draw this. Now let's pay attention here. 18 now. Okay, just take the question. I want to move to a new page so that we can get a much bigger space to draw it. Okay, let me put it here. Mhm. So that we could see it very well. All right. So I want to draw my axis here. It's not straight, but pardon me. So this is my axis. Let me extend it here. This is my row. My row. This is my imaginary. I know that this axis will be positive and the rest. So let me graduate it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me erase it and extend the line because you could see that let me extend this line here. So 10, 11, 12, 13, and there's my row. I have my -1, -2, -3, -4, -5, -6, -7. I have my 1, 2, 3, 4, 5, 6, 7. I have my -1 here, -2, -3, -4, -5, -6, -7, -8, and -9. Right. So let's take the first. Now, the reason why I'm doing this is that I want you to understand the whole concept of how we are able to change complex numbers in the complex form to the polar form. So you see that complex numbers in the rectangular form. So this is the rectangular form of complex numbers. How are we able to change it from this form to the polar form? So we need to understand this thing. So here, let me take a red color to depict complex number 1. So on the real side, it is what? 4. So I locate my 4. This is my 4. On the imaginary side, it is negative. So I come down. So -3. So it is somewhere here, right? Somewhere here. So I put my dot. Then I draw a line, a straight line from the origin. A straight line from the origin to that point, right? Now, if I extrapolate this, extrapolate that, the angle here, let me call it this thing. The angle here, let me call it θ1. Now, because this is a line, it will have a magnitude, right? Let me call it Rm. That is Rm. Do you get it? All right. So this θ1, or the angle that we know, we in terms of angle, we measure it with respect to the real axis or the x-axis. So yeah. So this angle is what we call the argand. The argand. So let's take note. Now let's take complex number 2. This complex number is a complex number. It's because you are not seeing the I because the I is 0. So this complex number is 4, but it's the same as 4 plus 0I. Do you get it? So how do you represent this? On the, I can't say, argand diagram. Let me use green. So the real part is 4. Here is it. And the imaginary part, is what? And the imaginary part is 0. This thing. And the imaginary part is 0. The imaginary, so this is where the real part is. This is where the real part is. The imaginary part is 0. So it should be on the real axis, right? Now, on this axis, what will be the angle? What will be the angle? The angle is 0, right? Because the line is on the real axis. The line is here. So there is no angle. So the angle here is what? Is 0, right? So let's take note. If I have only a complex number with only the real part, complex number with only the real part, and if the real part is positive, right, the argand is what? 0 degrees, right? Let's take note of this. If it is negative, the argand is 180. Now, the reason why we have to do this is because when we are changing this, uh, when we are changing this rectangular, this complex number in the rectangular form, mostly people will say that because when we are doing the change, we use formula. People will say that, oh, the argand does not exist, but it exists if we come to the argand diagram, right? But if in terms of formula work, you realize that it will not exist because you are going to get something over 0, which is undefined. Do you get it? But in terms of diagram, it is what? It is 0. Do you understand? That is why we need to understand the diagram representation of rectangular complex numbers. So I'm saying that if you have a complex number which has only the real part, right, and it is positive and the real part is positive, the argand is 0. If the real part is negative, assuming it was here, assuming assuming it was here, it was at this side, uh, this side, then the angle will be from here to here. Now, in argand diagrams, we measure the angle anti-clockwise. So anti-clockwise, you get it? So from here to here is going to be what? 180. That's why I brought this up. So take note. Now let's see the next complex number. Let me use the black color. See. So this is also a complex number. It does not have a real part, but has only what? An imaginary part, which is what? Negative was 6. So where is negative 6? On the x-axis is 0, so this is my 0 on the x-axis. And I look on the real axis, sorry, is 0, and I trace it to the imaginary axis, which is negative 6. So it is here. It is here. Here is it, right? Now for this, what would the angle be? So from here, anti-clockwise here, right? There is 90, 90, 90. That is 270. So if you have a complex number that has only the imaginary part, only the imaginary part, and it is negative, the argand is 270. If it is positive, the argand is 0 or 360 degrees. Hey, no, no, no. Oh, sorry. I think I was. It's supposed to be 90, not 0. Yeah. Forgive me. It's uh, it's 90. Let me erase it. Oh, it's 90 rather. Oh, sorry. It's 90 because if it is positive, it will be here. It will be here. It will be here, and that will be from here to here. So that is 90 degrees, right? So if I have a complex number that is made up of only the imaginary part, then I'm supposed to find the argand of it. Is If it is negative, the argand is 270 degrees. If it is positive, the argand is 90 degrees. Sometimes they'll ask you to change it to, how do you call it, radians, and we will learn how to do it. Then Z4, complex number 4, complex number 4 is made up of both real and imaginary. So the real is 2. So here's my 2. Here's my 2. And the imaginary is negative 8. So this is negative 8. So 2 and negative 8, if I trace it, they meet here. I draw a line through it. Right? So the distance from here to here is my magnitude, and the angle that will be measured from here to here. Now, because we measure anti-clockwise, if I measure it this way, that is the negative of the angle. I have to indicate negative. So if I want the actual measuring, it's like this, anti-clockwise. So go and try Z5 and what Z6. And when you're done, you can send it to me. So with this in perspective, we want to look at polar form of complex numbers. So I want you to relax your brain for a minute so that we continue. A minute. A minute so that we continue. So let's see some small recap of what we've done so far. I think here we started with the, the multiplication and division of complex numbers in the rectangular form. We looked at some theories and so on and so forth. So break is over. Let's continue. All right. So let's continue. Let's continue. Okay. So I want us to look at complex numbers. Complex numbers in the polar form. Most of the complex numbers thing that we are doing here, you could use calculator for most of the thing, but it depends on the lecturer that is teaching you. For me, my time, Dr. Kwabi was the one who taught us, and unfortunately, your calculator will be very useless at the exam. So yeah, because you cannot do anything with the calculator. The only thing you could do is add one plus one and the rest. So you need to understand it for yourself. And this course is a course that you have to you build upon. So aside learning how to pass the exams, you have to also learn and understand it. You get it? Because it's very essential. Next semester, you do other courses that you might or you'll be using complex numbers. There are some engineering courses, especially in the electrical field. You meet it, so you need to understand it. So initially we started with complex numbers in the rectangular form. Now you're going to look at complex numbers in the polar form. So just as I said, complex numbers are just like fractions. So you see fraction, we have decimal fractions, percentage, uh common fraction. So I can give you 50%, which is a fraction. I can ask you to change it to common fraction, which is what? 50 over 100. I can ask you to change it to decimal 0.5. So it's the same thing that we are just playing around. You get it? Or playing around it. So here we are going to learn how to represent complex numbers in the polar form. Now you remember the Argand diagram that we did? Yes, we are going to build on it. So assuming we have this as our Argand diagram, not showing the other part. So we have this our imaginary part and this our real part. Let this be my origin. Assuming I have a complex number z, which is a plus bi, right? And this is my a, this is my b. Now the b is here because it carries the I, the imaginary. So this is the imaginary part, it is here. So this is the point, this is the point. If I extrapolate, that's what the mathematics teachers have been. I don't know if it is a right English word, so which I'm using it. So extrapolate. So at this point, that is where the point meet, right? So from the origin to this point, it's a line. JHS, linear graph. Remember, we find the length of a line passing through 2 points, right? So if I have x is equal to a1, and sorry, I have a is equal to x1, y1, right? And I have b is equal to x2, y2, and I have this as my point, another point. This point A, point B. This line, I want to find the what? The length is equal to AB is equal to what? Square root of x, changing x squared plus changing what? Y squared, right? But here, our first point is the origin. So it's 0, 0. Have you seen that? 0, 0. So the idea in JHS. So yes, university is very simple. Anything. You get it? So we just import ideas from previous studies. So I have Z, or the complex number is equal to A plus B. This is my A, this is my B. So this is what? A line. So I can find the magnitude, right? So let me call this R, right? Let me call it R. Let me call it R. So if I'm calling it R, then R is equal to magnitude or length. But you see, the mathematics people, they want to show us that they are our guys, so they use another word called modulus. Modulus. So this R can be magnitude, can be length, can be what? Modulus, right? So our R, in terms of calculation, you can see that our R is equal to square root of A squared plus B what? Squared. So we can see that R squared is equal to A squared plus what? B squared. So this is how to find the magnitude of what? Of a complex number. You just take the real part, square it, add it to, take the imaginary part without the I and square it, and that will give you the magnitude. Then the angle here, who can tell me what it is? Type it. Who can tell me what that angle is? So that angle is a argument, or the argument. So the so theta, let me write it here. Theta is our argument, or the angle. The argument of what? Argument of z. So we can write it as this, or we can write it as arg what of z. Now if you look at this, if I want to find the angle here, trigonometry, right? So this is a right angle triangle. Trigonometry. From here to here is my A. From here to here is my B. So So we can find theta, right? So tan theta is the trigonometric ratio that expresses the opposite and the adjacent, right? So to a that is opposite over what? Adjacent. And what is my opposite? The face that is facing the angle, this angle, the face that's face. So that will be B over what? A. So if I want the angle, is tan inverse of what? B over A. Now it's not always that this formula will work, oh, especially when I give you Z1 is equal to I. And I ask you to find, I told you, remember when we're looking at the Argand diagram, I told you that sum of it, if you do the calculation, to give you undefined, right? So in that case, you have to rely on the diagram because here we have a situation. Let me erase this so that you could see it clearly. So if I have expression like this and assuming I have a complex number, z is equal to, let's say, 5i, it means that the real part is 0. So if I put 0 here, it's it will not be possible for me to find theta, right? So in that case, I have to go to the diagram. Where will 5i be? 5i will be here. And what is the angle there? The angle there is what? 90. Do you get it? So uh but if you are smart, you know that tan of 90, let me see, tan of 90, a smart error does not exist. So anything that will make this equation does not exist, it means that that angle is what? 90. You get it? So these are the two equations that we are going to work with. This and what? The argument tan inverse of what? B over A, which is tan inverse of the imaginary part over the real part. The imaginary part over the real part. Yeah, so we take some few example, then we end here. Then we continue another time. Few example. So let's see. Or some of you want to write. Let's those who want to write, you can, or you can screenshot it whilst we continue. So these two formulas will help us to find the magnitude and the argument, just the magnitude and the argument. We've not yet started transforming rectangular complex numbers in the rectangular form. We have not yet. We've not started that one yet. So let's see. So let's take some example. Find the modulus and argument of the given complex numbers in the rectangular form. So we have a number of complex numbers in the rectangular form. We are asked to find their arguments, and two, their modulo, that's the magnitude. So the first one we have is 4 plus 3i. Second one we have I. Third one we have let me get some examples from my note. We have minus 3 minus 4i. We have z4 to be equal to 5, and z5 to be equal to minus 5 plus 2i. So these are the complex numbers given to us to find. They are asked to find. So I think after this example we will end here so that another time we continue from there. Yeah. So they are asked to find their modulus and argument. So the first one, Z1, we have 4 plus 3i. So the modulo, that is the length of Z1, is equal to square root of 4, the real part square, plus the imaginary part. I take the number, only the number without the I, squared. And that is going to give me square root of 16 plus what? Plus 9. And that is square root of 25. And that is what? 5 units. Now, the argument tan inverse of the imaginary over what? The real. So tan inverse of 3 over 4. Tan inverse of 3 over 4. Punch it on your calculator. You can keep it in degrees, or you can do it in radians. So 3 on 4, tan inverse of it is 30. Is 36.869. If I want it in radians, I change my calculator to radians and I look for it. That is in radians is 0.6435 rad. So that is the first example, and this is what we've gotten. So for Z1, we have modulus 5 units and argument 36.869. So these two things, we will need it when we are finding the, how do you call it there, when we are changing a complex number to the polar form. I'll do the next one, then you take the rest as assignment, which I would want to see how you solve it. The next one, Z2, is what? I, right? So I, it means that the real part is 0, right? So the magnitude of Z2 is going to be square root of 0 squared plus what? 1 squared. And that is going to give us square root of 1, and that is what? 1, right? Now, the angle, the argument, tan inverse of 1 over 0, which I told you that this will give you mathematics error, right? Or math error. So with this, I have to go to the Argand diagram and find it. This is my imaginary part, this is my real part, right? This is 0, and so I is what? Negative, I is positive 1, or I is 1. And so the angle from here to here is what? 90. And so here my argument is what? 90 degrees, or in terms of radians, radians. Please, you recently came from senior high school, so you know it. Uh, so you can convert it. I think 2 pi is 360 degrees. Pi is what? 180, right? So 90 will be what? Pi on 2. Yeah. So that's it. So we'll end here. Take this as your assignment and go and try your hands on them. Thank you very much for joining. Thank you. I want to see if there is any question. Uh, all right, so we'll end it here. Thank you very much for joining.